August 12, 1942. Chesapeake Bay, Virginia. Lieutenant Commander William Sterling stood on the deck of the cruiser USS Cleveland, watching 3 radio-controlled drone aircraft climb into the morning sky. As gunnery officer, he had presided over hundreds of anti-aircraft tests during his naval career. None had generated the anticipation he felt that morning. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Loaded into Cleveland's 5-inch gun magazines were shells containing technology that the world's leading military powers had declared theoretically impossible. Inside each projectile's nose, packed into a space no larger than a wine bottle, sat a complete radio transmitter and receiver built with miniaturized vacuum tubes designed to survive forces that should have pulverized them into powder. The test was scheduled to run 2 full days. It would last less than 3 hours. Cleveland's gunners opened fire as the drones began their simulated attack runs. The first salvo missed by 70 feet. The second salvo struck close enough that shrapnel tore through the nearest drone's fuselage. The aircraft disintegrated without being directly hit, destroyed by a shell that had exploded precisely 28 feet away. 3 more bursts followed in rapid succession. Within minutes, all 3 drones had been obliterated from the sky. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Naval observers cancelled the remainder of the scheduled tests immediately. What they had witnessed that morning represented a revolution in aerial warfare. For 2 decades, anti-aircraft gunners had fired thousands of shells, hoping for a single kill. Cleveland's crew had just destroyed 3 maneuvering targets with fewer than 10 rounds. The mathematics of aerial combat had been fundamentally rewritten by a device that every major military power had concluded could not be built. The story of how American engineers succeeded where German, British, and Japanese researchers had failed begins not with brilliance, but with a problem that had plagued military forces since aircraft first became weapons of war. The challenge was straightforward to state, but seemingly impossible to solve. How do you make an artillery shell explode at precisely the right moment to destroy a target moving at 300 miles per hour? Traditional anti-aircraft fire required 3 pieces of perfect information executed in sequence under combat conditions. Optical rangefinders had to calculate exact distance to a target that might be maneuvering through smoke, clouds, or glare. Height-finding equipment had to estimate altitude against aircraft that could climb or dive at will. Fire control computers then had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach altitude. A sailor manually set a clockwork time fuse by turning a wrench against a mechanical mechanism while enemy aircraft screamed overhead. The shell was loaded, the gun fired, and the fuse mechanism counted down. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly, the shell would explode near the target. The odds of destroying an aircraft were approximately 1 in 2,500 rounds fired under ideal conditions. In actual combat with multiple targets maneuvering through defensive fire, the odds dropped catastrophically. Some estimates suggested it required 100,000 shells to down a single enemy aircraft. The human cost of this inefficiency was measured in lives and ships. December 7, 1941, as Japanese aircraft attacked Pearl Harbor, American gun crews fought back with everything available. 5-inch naval guns thundered from damaged ships, hurling shells skyward at attacking dive bombers and torpedo planes. Most shells exploded harmlessly in empty sky, their preset timers detonating them seconds too early or too late. Some never exploded at all. Others fell back to Earth, their contact fuses still armed. In Honolulu, 9 miles from the harbor, 55-pound shells crashed through roofs, detonated in streets, tore through buildings. The Yumori family died when a 5-inch shell flew through their restaurant window during breakfast service. By the time smoke cleared over Pearl Harbor, 68 civilians lay dead. 32 of them had been killed not by Japanese bombs, but by improperly fused American anti-aircraft shells landing in the city. The tragedy illustrated with brutal clarity the inadequacy of existing technology against modern aircraft. The concept of a proximity fuse had tantalized military engineers for decades. Make a fuse that could detect when it approached a target and detonate automatically. Simple in theory, impossible in practice given the technology of the 1930s. Germany had explored proximity fuses as early as 1930, developing over 30 different designs. These included acoustic sensors that would trigger on engine noise and electrostatic detectors that would respond to charged aircraft surfaces. By 1939, German researchers had concluded the technical challenges were insurmountable. The fundamental problem was miniaturization. Any device capable of detecting a target and triggering a detonator required electronic components. The only electronic amplifying devices available in 1940 were vacuum tubes. These were fragile glass envelopes containing delicate filaments and electrodes. Standard radio tubes stood 6 inches tall and weighed several ounces. The largest tubes manufactured for rugged applications were designed for mobile military radios and could withstand 10 times the force of Earth's gravity during acceleration. A 5-inch artillery shell experienced acceleration of 20,000 times the force of gravity when fired. At 20,000 gravities, a 1-ounce tube would effectively weigh 1,250 pounds for the fraction of a second it took the shell to travel down the barrel. Forces sufficient to turn solid steel into fragments. Every major power that examined the problem reached the same conclusion. Electronics that could survive artillery launch were beyond current technology. The British had reached furthest. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a small Doppler radar system. They tested prototypes on rockets, which faced far less severe acceleration than gun-fired shells. But Britain's program was stymied by 2 critical obstacles. The cost was astronomical, and Britain's industrial capacity was already stretched to breaking. More fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available, those used in hearing aids, were still far too delicate to survive the violent acceleration of being fired from a gun. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was inadequate. The British shared their research through the TIZAD mission when America entered the war. But it would be American scientists and American industry that actually made it work. The man who would solve the impossible problem was not a weapons designer or military engineer. Dr. Merle Anthony Tuve had spent his career exploring the physics of the ionosphere using radio waves. Born in Canton, South Dakota, in 1901, he had studied at the University of Minnesota and Johns Hopkins University before joining the Carnegie Institution's Department of Terrestrial Magnetism in Washington. In 1925, working with Gregory Bright, Tuve had pioneered techniques for measuring the reflection of radio waves from the ionosphere to map its structure. This work laid the theoretical foundation for radar. When the National Defense Research Committee approached him in August 1940 about developing a proximity fuse for artillery shells, Tuve understood immediately that radio physics might provide the solution. His proposal was elegant in concept. A miniature radio transmitter in the nose of the shell would emit radio waves at approximately 180 to 220 MHz. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect. When the reflected signal reached a predetermined frequency, indicating the target was within lethal range, an electrical circuit would close and detonate the shell. The theory was straightforward. Making it work was another matter entirely. Consider the engineering challenges that faced Tuve and his team. The fuse had to fit into the nose of a 5-inch artillery shell, leaving room for 7 pounds of high explosive. Inside this space, engineers had to fit a complete radio transmitter and receiver, a power source, safety mechanisms, and a detonator. All of this had to function in extreme temperatures ranging from Arctic cold to tropical heat and survive storage for months. Most daunting of all, it had to withstand the shock of being fired from a gun. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity. Every component experiences a crushing force equivalent to being hit by a sledgehammer. The shell then spins at 25,000 revolutions per minute as it passes through the rifled barrel, and after surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target. The project, designated Section T of the National Defense Research Committee, began on August 24, 1940, with Tuve as chairman and a handful of researchers in a laboratory at the Carnegie Institution. Security surrounding the work was absolute from the beginning. Workers signed secrecy oaths. The cover story described research into optical instruments. The reality was a crash program to develop a weapon that Allied military leaders believed could alter the course of the war. Tuve's first recruit was James Van Allen, a young physicist from Iowa Wesleyan College, who would later achieve fame for discovering the radiation belts surrounding Earth. Van Allen joined the Applied Physics Laboratory in April 1942 as a founding member. His assignment was to develop what the team called rugged vacuum tubes. He started with miniature tubes that Raytheon and Sylvania had developed for hearing aids. These were designed for the gentle environment of sitting in someone's pocket, not the violence of artillery fire. Working with Sylvania Company engineers, Van Allen redesigned the tubes from first principles. The glass envelopes were thickened and carefully annealed to increase strength. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections to distribute forces more evenly. The tubes were potted in wax inside the fuse body, which cushioned them against shock. Every aspect was tested by firing complete fuses from a vertical gun into the ground at the Naval Proving Grounds in Dahlgren, Virginia. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The soft earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see what had broken. Through hundreds of test firings and thousands of design iterations, the team gradually developed tubes that could survive. The breakthrough came not from a single innovation, but from systematic refinement of every detail. Glass composition was modified with additives that increased strength while maintaining the vacuum seal necessary for tube operation. Internal components were embedded in shock-absorbing materials. Electrode structures were redesigned using spot welding techniques that created mechanical bonds capable of surviving extreme stress. By September 1941, Van Allen's team was achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up, and they were right. By early 1943, reliability had climbed above 90%, but vacuum tubes were only one challenge among many. The fuse needed a power source. Conventional batteries were too large and had limited shelf life, particularly in tropical heat. Engineers Harry Diamond and Wilbur Hinman at the National Bureau of Standards developed an ingenious solution called a reserve battery. The device used a liquid electrolyte kept separate from battery plates until activation. When the shell was fired, centrifugal force spun the electrolyte into contact with the plates, generating electricity. This gave the batteries indefinite storage life and provided a built-in safety mechanism. The fuse needed multiple additional safety mechanisms. It could not arm until well clear of the gun. It required protection against accidental detonation from radio interference or the ship's own radar. It needed wave suppression circuitry to prevent premature detonation when fired at low angles over water, where reflections from the ocean surface could trigger the fuse prematurely. Each safety feature added complexity and consumed precious space inside the fuse body. The antenna design presented its own challenges. Engineers developed a ring antenna circling the fuse body that was small enough to fit in the nose, while efficient enough to transmit and receive radio signals. The transmitter circuit had to generate radio frequency signals using just 3 vacuum tubes. The receiver circuit had to detect signals 1/millionth the strength of the transmitted signal. Amplifier stages using 4 vacuum tubes provided sufficient gain. The Doppler detection circuit compared transmitted and received frequencies, closing an electrical contact when the difference indicated proximity to a target. This circuit represented some of the most sophisticated electronics of the era, all miniaturized to fit inside a space measuring 8 inches long and 2 inches in diameter. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components. The Mark 32 fuse for the Navy's 5-inch gun weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. The device represented the absolute limit of what contemporary technology could achieve. The transformation from laboratory prototype to combat-ready weapon required solving not just technical problems, but industrial ones. Tuve understood from the beginning that developing a working fuse meant nothing if it could not be manufactured by the millions. Every design decision prioritized manufacturability alongside functionality. Components were standardized wherever possible. Assembly procedures were simplified. Testing protocols were developed that could identify defective fuses without requiring skilled technicians. 5 companies were selected to manufacture the fuses under license from the Applied Physics Laboratory: Crosley Corporation in Cincinnati, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris each. They received contracts to establish dedicated production facilities. Over 100 additional factories participated in some phase of component production. The supply chain eventually involved over 2,000 suppliers providing specialized parts. Production started slowly. By the end of 1942, factories were producing 500 fuses per day. But American industrial capacity was just warming up. By late 1943, production had reached 40,000 fuses per day. At peak output in 1945, American industry was manufacturing 70,000 proximity fuses daily. Over the course of the war, American factories produced more than 22 million proximity fuses at a cost exceeding $1 billion 1940s dollars. The Crosley Corporation in Cincinnati alone produced 5,259,113 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously 7 days a week, achieving peak output of 16,500 fuses daily. Sylvania Electric Products in Ipswich, Massachusetts, produced even more, manufacturing 5,683,332 fuses, while also producing 95% of all miniature vacuum tubes used across the program. Thousands of workers, many of them women, assembled the intricate components under conditions of absolute secrecy. Workers signed secrecy oaths and were searched entering and leaving the facilities. They did not know what they were building. Security surrounding the proximity fuse was second only to the Manhattan Project. The device was given the deliberately misleading code name VT Fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. The very existence of the fuse was classified top secret. Even its use in combat was initially restricted to situations where there was no chance of a dud falling into enemy hands. The Pentagon strictly forbade use of the fuse over land. The risk was too great that a dud shell would fall into enemy hands, where German or Japanese engineers might reverse engineer the technology or develop countermeasures. Intelligence analysts estimated that if Germany equipped its anti-aircraft guns with proximity fuses, bomber losses could increase by 300%. The strategic air campaign might become impossible, so the fuses were used only over water, where dud shells would sink beyond enemy reach. The first combat use came on January 5, 1943, off Guadalcanal in the Solomon Islands. 4. Japanese Aichi-D. 3 A-dive bombers attacked a United States Navy task force. As the aircraft broke off their attack, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the cruiser USS Helena, fired 3 salvos of proximity-fused shells at the departing bombers. All 3 shells exploded near one of the aircraft, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners had achieved what would have required dozens or even hundreds of conventional shells. They had downed an enemy aircraft without scoring a direct hit. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. The fuses proved 3 times more effective per round than conventional time fuses under identical conditions. Against fast-moving targets in night engagements, the advantage increased to 7-fold. Admiral Arleigh Burke, who later served as Chief of Naval Operations, recalled that when he served as Chief of Staff to Admiral Mark Mitcher commanding the fast carrier task forces, proximity fuses knocked down enemy planes by the dozens. Ships that had previously relied on volume of fire to create walls of steel could now achieve aerial kills with a fraction of the ammunition expenditure. The effectiveness triggered Japanese tactical changes that Allied intelligence observed, but could not fully explain. Japanese aircraft began attacking from higher altitudes, sacrificing bombing accuracy to remain outside effective range. Torpedo bombers approached at wavetop altitude where radio reflections from the ocean surface caused premature detonations. Dive bombers released at steeper angles to minimize exposure time. These adaptations reduced Japanese strike effectiveness while failing to restore the advantage they had enjoyed earlier in the war. The true test came when Japan, facing inevitable defeat, implemented a strategy born of desperation. In October 1944, Special Attack Units, officially termed Shinpu Tokubetsu Kogeki Tai but known universally as kamikaze, began deliberate suicide attacks against American ships. The first organized kamikaze attacks struck during the Battle of Leyte Gulf. The tactic was born from Japanese recognition that conventional attacks had become ineffective. Experienced pilots had been systematically destroyed over 2 years of attrition. Replacement pilots received minimal training, insufficient for bombing and torpedo attacks that required precision. Kamikaze attacks required only enough skill to keep an aircraft pointed at a target. Proximity fuses proved essential against kamikaze attacks, though their effectiveness was complicated by the nature of the threat. Conventional attacks saw aircraft approach, release weapons, and attempt to escape. Proximity fuses destroyed attackers at distances where damaged aircraft would miss their targets. Kamikaze attacks removed the escape phase. Pilots flying damaged aircraft continued toward targets, sometimes surviving long enough to crash into ships even after sustaining damage that would have caused conventional attackers to abort. The solution required concentration of fire that destroyed aircraft completely rather than merely damaging them. Ships increased rates of fire, created denser patterns of proximity-fused shells, and engaged targets at longer ranges. The results were documented in one of the most intense naval engagements of the Pacific War. May 11, 1945, off Okinawa. The destroyers USS Hadley and USS Hugh W. Hadley, operating as radar pickets, came under assault from approximately 150 Japanese aircraft during Operation Kikusui No. 6. Many were loaded with explosives and intent on suicide runs. During approximately 1 hour and 25 minutes of intense combat, the 2 destroyers and 4 support craft faced overwhelming odds. Hadley knocked down 23 enemy planes before being hit by 1 bomb, 3 kamikazes, and 1 Oka rocket bomb. Hugh W. Hadley accounted for additional aircraft before being hit 4 times by suicide planes and left dead in the water. Both ships survived despite catastrophic damage. The post-action report's verdict on proximity-fused ammunition was unequivocal: indispensable. Without proximity fuses, both ships would certainly have been sunk in the first 30 minutes. Statistical analysis from the Pacific War documented the effectiveness precisely. Between October 1944 and August 1945, American naval forces destroyed 278 Japanese aircraft using proximity-fused ammunition. Analysis showed that only 46 would have been destroyed using conventional time fuses under identical circumstances. The 6-to-1 effectiveness ratio translated directly to lives saved and ships kept in action. But for most of the war, the Pentagon's absolute restriction against land use remained in force. That calculation changed in June 1944 when Germany unleashed the Von flying bomb against London. Launched from sites across the English Channel, the V-1s approached at speeds of 400 miles per hour, faster than many Allied fighters. Small, fast, and arriving without warning, they were extraordinarily difficult to intercept. From June to late August 1944, Germany launched over 9,000 V-1s against Britain. The pilotless missiles inflicted tens of thousands of civilian casualties. British defences initially could destroy only 17% of the V-1s that entered the coastal gun belt. The situation was desperate. Prime Minister Winston Churchill authorised use of proximity fuses in anti-aircraft guns defending Britain, accepting the risk of technology compromise. Modified fuses were rushed into production, specifically calibrated for the small, fast V-1s. British and American anti-aircraft guns along the coast were equipped with proximity-fused ammunition, working in conjunction with new radar systems and fire control computers. The effect was dramatic. Within 4 weeks, the destruction rate climbed to 74%. During one day in late August, 82% of incoming V-1s were shot down. Churchill later stated that the proximity fuse made possible the successes that anti-aircraft command was obtaining. The Von campaign demonstrated beyond doubt that the proximity fuse was war-winning technology, but it also meant the secret was partially compromised. Thousands of fuses were being fired over land. The risk that had seemed so unacceptable in 1943 now had to be weighed against military necessity. In December 1944, that calculation changed completely. On the morning of December 16, 1944, more than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's last desperate offensive in the West. The Germans struck through the Ardennes forest, aiming to split the Allied armies and capture the vital port of Antwerp. The offensive took the Allies by complete surprise. Within days, German forces had driven a bulge 50 miles deep into Allied lines. The weather was terrible, with heavy snow and thick clouds that grounded Allied air power. German commanders felt safe from artillery fire because poor visibility made accurate observation nearly impossible. They were catastrophically wrong. On December 16th, the same day the offensive began, Colonel Oskar Alfred Axelson, commander of the 406th Artillery Group, faced an agonizing decision. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. Axelson had just received a new type of ammunition, proximity-fused shells, codenamed POSIT, but Supreme Commander Dwight Eisenhower had not yet authorized their use over land. The secrecy restrictions were still technically in place. Axelson decided the emergency trumped the restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating. For the first time in the European theatre, American artillery was firing airbursts with perfect consistency regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. Foxholes provided no protection. The shrapnel rained down from above, penetrating even log-reinforced bunkers. German soldiers who had survived years of combat on the Eastern Front had never experienced anything like it. They could not hear the shells approaching due to the high velocity. The first warning was the explosion overhead. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Over the next 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theatre. The impact on German forces was immediate and catastrophic. Lieutenant General George Patton later wrote to the War Department, describing an action near the Sauer River. His Third Army had caught a German battalion attempting to cross with a concentrated barrage of proximity-fused shells. By actual count, 702 enemy soldiers were killed. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies had this weapon, they would need to devise entirely new methods of warfare. He added with evident satisfaction that he was glad the Americans had thought of it first. The morning of December 21st saw proximity fuses used in defense of Malmedy itself. SS Colonel Otto Skorzény's Panzer Brigade 150, part of the elaborate German deception operation, attacked the town at approximately 4:30 in the morning. American artillery battalions supporting the defense fired proximity-fused shells with devastating effect. The air bursts so unnerved the attackers that some charged directly into American positions seeking any shelter from the overhead explosions. The attack was repelled by afternoon. German prisoners of war, interviewed by American intelligence officers, captured the psychological impact. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer, focused on the implications for air defense. If Germany had possessed proximity fuses, he estimated the Allied strategic bombing campaign would have become unsustainable. At loss rates of 15 to 20% per mission, the combined bomber offensive would have ground to a halt. But he immediately added that Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match. The Battle of the Bulge demonstrated how American doctrine had evolved to maximize the fuse's effectiveness. Forward observers called down fire not just on visible targets, but on suspected positions. Artillery batteries laid down barrage patterns covering entire areas. The proximity fuses meant that every shell was an effective airburst. German tactical doctrine, developed over years of warfare, had to be completely rewritten. Traditional defensive positions were suddenly death traps. Moving in the open during artillery fire was suicide. The Germans tried to adapt by dispersing more widely and staying constantly on the move. But adaptation had limits. The proximity fuse fundamentally altered the equation. German soldiers began to exhibit what American intelligence termed artillery shock syndrome, a condition specifically triggered by the helplessness of facing proximity-fused fire. Some units experienced discipline problems, with soldiers refusing orders to move into areas under American artillery coverage. American intelligence reports noted that German commanders were offering rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. The Germans never fully grasped what they had captured. When German forces overran an American ammunition dump during the Battle of the Bulge, they seized approximately 20,000 proximity fuses. German ordnance experts examined the devices, but concluded they could not possibly function as intended. The technical specifications seemed impossible. Electronics that could survive artillery launch forces were considered beyond current technology. Having concluded that radio-based proximity fuses were impossible given artillery acceleration forces, German engineers never fully comprehended that miniature radio transmitters were inside every shell. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impossible barrier. Ground combat intensified as well. During the Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity fuses set to detonate at rooftop level showered entire city blocks with shrapnel, making defensive positions untenable. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe would have proven exceedingly difficult and perhaps impossible. The counterfactual was chilling. German anti-aircraft defenses equipped with proximity fuses might have made D-Day landings unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance. The technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated. The Kranich acoustic fuse used a mechanical tone filter connected to a resonating reed switch. Rheinmetall Borsig developed an electrostatic fuse using capacitive detection. There were optical fuses, magnetic fuses, and experimental radio fuses similar to the American design, but none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired. But by then it was far too late. Germany lacked the industrial capacity to set up mass production. Even if production facilities could have been established, the resources required would have competed with production of tanks, aircraft, and basic ammunition. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. The proximity fuse alone consumed over $1 billion 1940s dollars. This included not just research and development, but building dedicated production facilities, training tens of thousands of workers, and maintaining absolute secrecy around the entire program. The production statistics were staggering. At peak output, American factories were producing 70,000 fuses per day. That represents nearly 3 billion individual components manufactured to precise specifications, assembled, tested, and shipped to combat theaters around the world. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, increased efficiency, and economies of scale. At $18 per fuse, the weapon was expensive, but not prohibitively so. The increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect, since the shell itself cost the same regardless of fuse type. Paying extra for a fuse that multiplied effectiveness was an obvious value. The secrecy was so complete that production workers at different factories did not know other facilities were building the same components. Suppliers manufactured parts without understanding their purpose. The security classification remained in force until September 1945, when the war ended and the proximity fuse was finally revealed to the public. For German prisoners of war who witnessed the defense against Von flying bombs while held in Britain, the revelation of what they had faced was profound. They could see anti-aircraft guns firing and V-1s exploding in mid-air. They understood that the same technology that had devastated their forces in the Ardennes was now protecting British cities. The psychological impact was similar to what German prisoners held in America experienced witnessing American industrial production. It was a realization that they had been fighting an enemy with resources so vast that German efforts could never match them. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding. One former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war. Not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem that Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources that Germany could not match. If America could build miniature radios that fit inside artillery shells and worked after being subjected to forces that would destroy normal electronics, what else could they build? The officer's conclusion was that Germany had been fighting a war of the 20th century with outdated assumptions about what was possible. The proximity fuse demonstrated multiple technological advances that would shape the post-war world. Miniaturized vacuum tubes required breakthroughs in material science, particularly in glass composition and annealing techniques. The printed circuit boards used in later production runs were among the first mass-produced examples of a technology that would revolutionize electronics. The reserve battery design using centrifugal activation was innovative and found applications in other military systems. The radio circuitry was elegant and efficient, pushing the boundaries of what could be achieved with vacuum tube technology. But perhaps the most significant advance was in manufacturing and quality control, producing millions of complex electronic devices with consistent quality-required systems and processes that barely existed before the war. American industry developed statistical quality control methods, automated testing procedures, and supply chain management systems that would become foundations of modern manufacturing. The workforce training programs were equally significant. Tens of thousands of workers, many with no technical background, were trained to assemble intricate electronic devices under microscopes. James Van Allen, the physicist who helped develop the rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958 and credited with discovering the Van Allen radiation belts, used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. The technology transfer went beyond space exploration. Engineers who had worked on proximity fuses went on to careers in the electronics industry, bringing expertise in miniaturization, quality control, and mass production. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions with enhanced reliability and performance. Modern weapon systems use descendants of the World War II proximity fuse. The Phoenix missile, the Standard Missile family, and the Patriot surface-to-air missile all use proximity fuses based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys and operate in jamming environments, but the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The story of the proximity fuse is ultimately a story about resources, priorities, and the different paths nations took through World War II technology development. Germany invested heavily in advanced weapons like jet aircraft, ballistic missiles, and advanced submarines. These were impressive achievements that demonstrated German engineering prowess, but they came too late and in too few numbers to affect the war's outcome. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.